Okay, 3, 2, 1, let's go. Alright, so let's wrap up the story of systems of differential equations. Alright, so the goal has been to learn how to solve equations that look like x prime is equal to ax plus f, where all of those represent matrices. A is a coefficient matrix, matrix involving numbers. X consists of our unknown functions, depending on an independent variable t, and f is the non-homogeneity, these other functions of t that might be showing up to the party. Alright, so we've already discussed how to solve the homogeneous version, where f is equal to 0, so specifically x prime is equal to ax, find the eigenvalues for a and the associated eigenvectors, and that tells you how to create solutions. Alright, so we already know how to do that. So now the question is, how do you find particular solutions? And what we're going to do is draw inspiration from the non-homogeneous case for second order and higher linear differential equations. So if you let your mind float back, you remember that we had two methods there. So we had undetermined coefficients and variation of parameters. And as we saw there, there's pros and cons to both of them, and we expect a similar story to happen here. Alright, so let us consider x prime equals ax plus f, where a is the very beautiful symmetric equation, matrix 1, negative 2, negative 2, 1, and our non-homogeneous piece involving the variable t, but not involving our unknown functions, negative 9 t and negative 18 t. Alright, so in this case, we're dealing with the 2x2, and as we did for non-homogeneous, we'll stick with 2x2s and note that everything we're doing does scale to 3x3s and bigger, but as we'll see, you're probably not going to want to do those by hand. Alright, so undetermined coefficients, the idea was to guess something that looked like the non-homogeneity and plug it in and hope it worked. So if I look at my non-homogeneity a little bit more closely here, I realize that it kind of looks like a polynomial, right? It's a constant term, and then there's a variable t, right? Note, I could factor the t out. So we've got the constant vector negative 9, negative 18, and we can think of that as being like a coefficient for t. So it looks like a polynomial. It's a first-order polynomial. So we should guess something that looks like that, but it's not quite a usual polynomial, because now, instead of the coefficients being numbers, instead they're constant vectors. Interesting. So that's what we're going to guess, because that's what f looks like, and right, our experience with undetermined coefficients tells us that we should throw in this plus v term, because if we're missing it, it's probably going to be a problem. So let's go ahead and plug this into the equation. Oh, there we go, I just did it. Now, there are some things to note, some ins and outs and what have you. So note that when taking the derivative, we have tu plus v. The derivative there is with respect to t. Now, note that the derivative of v with respect to t, v is a constant vector, so its derivative, well, right, it would be 0. There's no dependency on t, so the derivative there would be 0. Gets rid of it. And the same thing, the derivative of t times u, that would just be u, because our experience with derivatives says that if you've got a constant times t, the derivative would just give you the constant part. Okay, so we're playing a little fast and loose here with derivatives of vectors, and that's all right. Basically, our intuition from before of how derivatives work is just going to play fine here. We're going to get a little saucy with that in a little bit, so keep that in mind. Alright, and now, so that's the left-hand side. We get our u after taking the derivative, and when we plug it into our ax plus f, we get this, and then note how I pull it apart. I mind my p's and my q's. I get all my terms involving t together. Note here, I abuse the fact that I can pull scalars out of matrix multiplication. Again, completely legal. And yes, in this case, t is a scalar. Even though it is a variable, in our eyes, it is a scalar. So we're allowed to pull it in and out like that. Okay, so what do we have here? Well, we have this term on the left, and we have this term on the right. The term on the right is a t, but the term on the left doesn't. that means this piece right here has to equal a 0. And you can see when you highlight here, you get these weird, like, yeah, look at that. And the AV has to line up with U, so in other words, I have to have these two sets of matrix equations. All right, so here U and V are being represented with the vectors U1, U2, V1, V2, respectively. All right, now, how do we solve these? Well, we're going to solve the one on the left first, because the one on the left I can rewrite as a collection of linear equations, right? Again, the whole reason for this matrix notation is to streamline dealing with systems of linear equations, which are a frequently occurring phenomena. All right. Take a Coke Zero break, and let's get right back into it. So, you could solve these, and in fact, actually, this thing that I have set up here, I could turn that into an augmented matrix and do raw operations if I really wanted to get extra linear algebra, but we don't need to do that. If that sounds like a good time, then you should take Math 207, or Math 317, or Math 407. It just, the fun keeps going. Alright, and then here you could solve U1 and U2. U1 is negative 15, U2 is negative 12. And then we do the same thing, plug that into the second matrix equation right here. We now know what U1 and U2 are, and we can use that to solve for V. Specifically, you'll find that V1 is 13 and V2 is 14. All right. Excellent. So, as we discussed, this was a particular solution to this non-homogeneous differential equation. X of p we guessed was a t times u plus v. We were able to solve for u and v. And you can plug this in and check that it actually works, so go ahead and do that. So, oh, hey, negative 12 plus, oh man. You know, I go through these slides ever so carefully. And you know, and I do a dry run, you know, but even still, I always find there's always something wrong. No matter what, yeah, this is, I don't know. I've talked to other mathematicians about this, because it's like, you know, in your head everything makes sense, but then when you write it down, all of a sudden, yeah, even like published math papers, you're guaranteed there's an error somewhere that somebody didn't notice. Actually, in my field of research, here's a little coffee break for you. There's a very famous paper. I'm not going to name names or anything, but the paper claims something is true, and they give this example. And when I was in grad school and I was reading it, and I was looking at it, I'm like, this doesn't seem right. This seems like this is completely wrong. And I was at a conference where the author of the paper was there, and I went up to him like, hey, I was reading that paper, and I don't think that example's right. And then he just totally stone-faced goes like, oh yeah, no, that's wrong. Everyone knows that's wrong. I was like, wait, what do you mean everyone knows it's wrong? It's like referenced in other papers. Well, you know. Anyway. Alright, so speaking of things going wrong, see, connected it to what we were actually talking about. This method may fail, right? And that is our experience with undetermined coefficients. Sometimes our guesses don't work. So, for example, here is a matrix equation. Now, right, we should immediately be suspicious. There's a row of all zeros, and depending on the context, it's either a good thing or a bad thing with matrices. Sometimes you want to see that, other times you don't. This is one of those times where it's rather not have that. Now, since the non-homogeneity is a constant vector, seems like we should guess a constant vector. Well, why wouldn't you just guess that, other than it's not going to work? Oh, no, it doesn't work. You get 0 equals 2. Right? So if you do plug that in, you will get these equations, and yeah, those don't work out. Now, why did it not work out? So if we let our mind float back, the reason guesses can fail is that sometimes the thing we guess is actually part of the homogeneous solution. So let's actually solve for the associated homogeneous, which would be this differential equation, which has this as a solution. You can check that it does. And then let's note that the first part here is exactly what our guess would have been, a constant vector. So plugging that in would solve the homogeneous, which means it can't possibly solve the non-homogeneous differential equation, because it's a solution for the homogeneous. So plugging it in would just give you 0 equals f, but we know that's not true. Yes. So we need to make a better guess. And by experience of undetermined coefficients from before, we would just say multiply by t and hope it works. So if we do multiply by t and plug it in, note that you get this. So when you take the derivative, the t goes away and you just get u, so u1, u2. Now be very careful here, you're plugging in tu. So there's a tu1 and a tu2. Times 1, add them up, and then subtract off 2, which is exactly what I've written right here. And there's zeros down in that row, so it doesn't do anything, and we get this. So now we'll have some equations that we'll have to work with, right? So now, note, it's getting a lot more involved here, right? There's a lot more now maneuvering that I'm going to have to do. So I've got these two sets of equations, and a priori, before we go ahead and solve this, we shouldn't believe that this would work, right? We're just guessing that this should end up working. And if you got a keen eye, you see that it's going to work, because the second one just tells me that u2 is 2, plugging that into the first gives me that, and then I can rearrange it and get this. And conveniently, even though I have a polynomial that's identically to 0, the coefficients are equal. So the only way that happens is if those two equations are 0, which is equivalent to u1 being negative 2. Okay, so, it did actually work out in this case, but note, right, there's even less guarantee that it's going to work now than in the undetermined coefficient case for the second order linear and higher differential equations. So here we see it's a lot more perilous, right? There's so much more potential for things to go haywire, and the fact that everything worked out here is because I picked the problem out of the textbook, so it's supposed to work. Allegedly supposed to work. Don't trust your textbook. There's very classic examples of totally wrong homework problems. But anyway, so from now here we can then tell you that x sub p is precisely that negative 2t and 2t. Alright, great. So that's how undetermined coefficients is going to work, and as you can immediately see, it's got the same pros and cons as before. So pro being that it's, as we're going to see, it's a lot quicker than the other method, variation of parameters. The big con being that your guesses, the method of guessing for matrix equations is a lot more difficult, and there's a lot more material going around, and definitely a lot more arithmetic and algebra, and thus plenty of places to screw up a minus sign, and then that bridge collapses, or the space shuttle explodes, or it's all not good. All right, so that's the world of undetermined coefficients. So let's talk about the world of variation of parameters. So we want to mimic what we saw. Now, what we did before was, well, you'd have an equation. So, for an example, take your homogeneous equation, get the general solution, and variation of parameters said replace the scalars with variable terms. Let the parameters vary, hence the name. Excuse me. Now, we could do that, but we can make it look a lot sleeker in this case, right? Rather than looking at the general solution as these sums of vectors scaled, I should view it as a matrix multiplication instead, where phi is what's known as the fundamental matrix. So the matrix that is formed by taking these vectors, x sub 1 to x sub k, and smashing them together. So each one of those forms the columns, and the bold C here is just the coefficients. So rather than replacing C1 to Cn with unknown vectors V1 to Vn, which we need to be careful about how we choose that, instead we're going to do this, and we're going to let C vary. So we're going to do this matrix times a vector that is allowed to vary. Alright, so we are going to then guess that a particular solution looks like the fundamental matrix, the matrix that is formed by taking the solutions, smashing them together into columns, and taking them as the columns for the matrix, and then we're going to replace C with a vector V that we're going to allow to have unknown functions in it. So C has constants, V will have functions. We're letting it vary. Okay, so if we plug this into our equation, so note, taking its derivative, phi has functions, v has functions, so it is a product rule that will occur on the left, and the product rule. And the one thing on your textbook notes, and it's a good thing to keep in mind here, we got to make sure the dimensions are lining up when you write out your matrix multiplications, because this is a matrix and v is a vector, so it needs to be written this way. Okay, well, right after we write it out and look at it like this, that doesn't seem like that made anything easier. But let's talk about phi prime for a moment. A times the fundamental matrix times C. Fundamental matrix times C is the homogeneous, which means that A times homogeneous should be the derivative of the homogeneous. Now, C is a constant, so its derivative should just be the derivative of the matrix phi times C. And the only way this is going to fly is if phi prime is a phi, right? So that C there, right, is an arbitrary constant. So the only way that's going to work is if a phi and phi prime line up. So if I take that and plug that into my equation up here, that gets rid of this phi prime for me, and conveniently gives me the exact same thing on both sides of the equation. Isn't that beautiful? So those two knock each other out, and then I get phi, v prime is equal to f. V, again, remember, is the thing I'm trying to solve for. Phi is a fundamental matrix. The fundamental set of solutions, remember, those have to be linearly independent. They're the columns of this matrix. That means that matrix is invertible, so I can multiply both sides by the inverse of the fundamental matrix, and then you integrate to solve for v. And there we go. So if you want to get a particular solution, the variation of parameters method, first of all, note, much easier to derive than it was to derive it for the second order linear and higher. Right, that was a time-consuming result. Here we see it goes much smoother, and note that basically you solve the homogeneous, and we use it explicitly to solve. Alright, now, as clean and beautiful as this formula is, as we're about to see, doing it by hand is tedious, to say the least. So even though in terms of like an equation, it's really clean and crisp, in practice, it's a lot of stuff. So let's get an example, let's get our beak wet, and see how it goes. Okay, let's give it a try. There you go, that seems pretty innocent. How hard can this be? And you know, I'll be even nicer to you. I'll tell you what the homogeneous solution is. It's that right there. Trust me, I did it. Now note how I rewrote it. I rewrote it as a matrix multiplication. And that's another one of the very powerful things about using matrices, is that they let you view linear systems of equations as a vector equation, scale orders of vectors being added together, and also as a matrix multiplication. So there's just so many different ways of viewing the exact same thing. That's always a good thing. And here we see it on a full-out display here. So note that this matrix, 3et, e to the negative t, e to the t, e to the negative t, that's our fundamental matrix. Right there. Right, so those are the columns, the x1s and the x2s, the column vectors that we get here, smashing them together into a 2x2 matrix. Okay. And, oh, hey, a 2x2 matrix, and I know it's invertible. I have a formula for its inverse, and right away, we start feeling a little grungy, maybe, or a little. So, like I said, it's tedious to do this by hand. That's why we're going to stick to 2x2s. I'm not even my worst enemy when I make them do a 3x3 by hand. If it was a 3x3, it'd be very nice. But anyway, so we get the inverse. It's that right there. Is that the worst thing? I've seen worse. Alright, now what do we have to do? Well, now we need to multiply that by f. Well, that's not too bad, because it's a 2x2 matrix times a 2x1. That's not bad. We're just going to get another 2x1. And, right, you just take the first row, do the dot product with the column. For second row, dot product with the column. Yeah, okay, not too bad. Then what do? Then we integrate. Okay. Again, not too bad. All exponentials. No, like, t times cosines of t's, so not the worst integrals ever. There they are. They're the integrals. There's some alpha fractions running around, but it's not the worst thing ever. Then what do we do? Well, remember, this is what v is equal to. And what did we say our particular solution was going to be? Well, phi times v. So now we got to do this. Alright, well again, it's a matrix times the 2 by 1, so it's not the worst thing ever, so you can do it out by hand, and you get that right there. And that is indeed a particular solution to our differential equation. That's a particular solution. There it is. Alright, so the variation of parameters method, in the matrix case, is quite nice. It's got a real, like, kind of beautiful formula, right? This phi times the integral of phi inverse times f, right? That's a neat looking formula. That's one of those formulas where you're like, I'm doing something, you know. Right? This is some serious math right here. So it's quite crisp as an equation, but as we just saw, in terms of computations by hand, these are a little tedious, but not the worst thing ever. Okay. And so there you go. So variation of parameters for matrices has, again, basically the exact same strengths and weaknesses. It's a formula. It always works. It's set up to just do what we want it to do. And the formula itself, again, is kind of nice looking. It's nice little beautiful equation right there. But just as variation of parameters for second order and higher worked, the actual computation part of it can get a little, but not the worst thing. Okay, and with that, systems of differential equations have been defeated. Now, of course, this isn't the full story. We've only looked at the linear ones, and the world awaits you. Go forth and solve equations. All right, so that is it for today, and I'll see you next time.